So now that we have discussed about the finite and infinite sets and the different types of sets and the basic definition of a set, we will continue to understand how sets can be represented through the diagrams. Now, the whole branch of sets is considered to be taken in the set form and the diagrammatic form. So let's see how the sets can be taken in the diagrammatic form. So they have different rules through which we take the sets in diagrammatic form. So when I take the sets in diagrammatic form, firstly, we know that a set is generally denoted with the capital letters of the English alphabets. So for example, I take the set A to be this, and let me consider the elements inside the set as, say for example, 1, 2 and 3. So we clearly know that the number of elements in this set is 3, the elements being 1, 2, 3. Now using this, how do I represent this in the diagrammatic form? What kind of a diagram I use is what we're going to discuss in this session. So generally, a set is denoted with a circle. In the diagrammatic form, I denote the set A with a circle, not exactly a circle, but a random circle, and then denote it with a set A. So in the diagrammatic representation, I assume the set to be in the circular form, and all the elements lie inside this region. No element crosses out the circumference of the circle, is how I understand the diagrammatic representation of a set. So the elements 1, 2, 3, for example, taken here for the set A, will definitely lie inside the circle as 1, 2 and 3. But these elements do not cross the circumference of the circle. So this is how I understand the diagrammatic representation of a set, with the learning outcome coming out as note sets are denoted by circular diagrams. As you can see here, sets are denoted by circular diagrams. The elements of the set lie inside the circle. All the elements of the set lie within the circle, is how I understand the diagrammatic representation of a set. Now, for a finite set, I have finite elements inside the circle in the diagrammatic form. If there are infinite elements, also there would be infinite elements inside the circle, covering the entire area of the circle considered for the given set. Now comes the question on how does we understand the infinite set as related to the universal set, because the next concept we are going to discuss is about universal set. For a given problem, the biggest set which we are going to consider in that situation is called the universal set. Say, if I take the universal set, the definition is, it is the biggest set considered for the given problem. So the universal set differs with the differing problem. It depends on the situation of the problem taken into consideration. Say for example, I take the set of natural numbers considered under real numbers, then the biggest set in case of natural numbers considered under real numbers is the real numbers. Therefore, the universal set in case of that example would be the real numbers. Or if I say considering the natural numbers under integers, then the biggest set out in case of natural numbers under integers is the set of integers. Therefore, the universal set would be the set of integers. So depending on the problems, the universal set differs, but now let's see how the universal set is represented in the diagrammatic form. Firstly, it is denoted with either u or mu. The first thing we need to understand is how do we represent the universal set? Say for example, I represent the set with a capital letter A, B, C or X, Y, Z, etc. Similarly, a universal set is also represented with a fixed symbol, and that stands as the standard universal symbol for any problem considered. So seeing the symbol, we can easily identify that the given set is a universal set. So it is denoted by U, or sometimes some mathematicians denote it with mu. We read this as mu, or we can also denote by U. Both mean the universal set, the biggest set of the given problem. Now next comes, how do we denote these universal sets diagrammatically? Here, the sets are denoted with a circle, and similarly, the universal sets also are denoted with some geometrical closed figures. And in case of universal sets are denoted diagrammatically by a rectangle. We generally denote the universal set with a rectangle. So if I write a rectangle, then I assume that this is the universal set, where I denote somewhere here. This indicates that this is a universal set, U or mu. This indicates that this is a circle, therefore a set with 3 elements, 1, 2, 3, taken as an example inside the circle. So here's how I understand diagrammatically the set and the universal set. A set denoted by a circle and a universal set denoted by a rectangle. Now that we have discussed about the sets and universal sets in diagrammatic representation, let's combine the set and the universal set together to see how diagrammatically both can be drawn at once. Say for example, I take here the set mu, or the universal set U, as 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I have the universal set with numbers ranging from 1 to 9 in order, and then say I have the set A with values 3, 5, 8, 9. Now my set A is with 4 elements 3, 5, 8, 9, and because it's mu generally denoted for the universal set, I assume that the universal set has all the elements from 1 to 9. Now with the definition of the universal set, which says that it is the biggest set, I understand this to be the biggest set and this to be the subset of this, the part of that. Now let's try to represent them in the diagrammatic representation. Now clearly I have the universal set denoted by a rectangle. So let's draw a rectangle in the stage 1. So taking the rectangle, which is denoted with the universal set mu, then the set A is denoted by a circle as taken in the previous session. Now because this is part of this, I draw a circle inside the rectangle, where this circle is set A and this rectangle is the set mu, the universal set. Now let me fill up all the elements of set A inside the circle A. So 3, 5, 8, 9 lie inside the circle, so that I get 3, 5, 8, 9 inside the circle. Now the remaining elements come outside the circle. The remaining elements in the sense the elements of the universal set which are outside of A. So 3 is already there in set A, so I don't include that. Then 5 is also already there in the set A, so I do not include even 5. Similarly with 8 and 9. So these elements are already filled inside the circle A, therefore the remaining elements are assumed to be outside the circle A, but inside the universal set mu. So I have the elements 1, 2, 4, 6, 7, and that is. So I have all these elements 1, 2, 4, 6 and 7 lying outside the circle and within the rectangle, and the elements 3, 5, 8, 9 lying strictly inside the circle is how I understand the set A and the universal set mu with the diagrammatic representation. So any problem given, we try to structure up the rectangle and the circle and then fill the elements accordingly with the mathematical rules as we studied out here. So now that we have studied about the universal sets and the sets in the diagrammatic form, similarly we will also identify the definitions of the subsets and the supersets. So initially, to start with the subset, what is a subset? What is basically the definition of subset when we understand it through the concept of a set is the biggest question of the session. As I see the word subset, I clearly understand with the word subset that it is a sub or the part of the given set. Sub is part and the set is itself. So the part of a set is a subset. So if I can just bring in the part outside the set, then that part is considered to be a set. To be more clear, let's see that with the diagrammatic representation. When I have the set A denoted by the circle, then if I want to find the subset of A, then let me draw a circle inside A, which is B. Then clearly I understand with this diagrammatic representation that B is part of A because B is totally inside A. Therefore, B is said to be subset of A. Is how I understand the difference between the subset and the set. So here B is said to be the subset of A because B is totally inside A. B is called the subset of A because it is totally inside A or part of A or part of A is how I understand. And mathematically, the notation for subset is A is subset of B is how I understand the subset concept. So A is subset of B is denoted with the symbol subset, the elongated C. Now let's take one example problem to understand this more clearly. So for example, I take the set A to be 1, 3, 5, 7, 9 and 11. Now I have my set B denoted with 3, 7, 11. Now how do I identify whether the given set B is a subset of A or the given set A is a subset of B? Is how we need to understand the concept of subsets. So as I clearly see through the example where the set A is given with the elements 1, 3, 5, 7, 9 and 11 and the set B given with 3 elements 3, 7 and 11. So if you wanted to identify this to be a subset, it is very simple that we draw the two different sets in the diagrammatic form, and if we find one circle inside the other, then immediately I can say that one set is subset of the other. This is set A consisting of the elements 1, 3, 7, 11, 5, 9. Yeah, these are the elements inside set A. Now the set B is with elements 3, 7 and 11. So I see clearly that this circle is consisting of 3 elements, 3, 7 and 11, denoted by B, and the whole set A is with the elements of set A, denoted with the bigger circle A. Now as I clearly see this through the diagrammatic representation, I understand that B is clearly inside A. If B is inside A, then B is called subset of A. If A is inside B, A is called the subset of B, vice versa. Since in case of this, all elements, or you can directly say, since set B is inside set A, therefore the set B is subset of A, is how I understand the subset concept. Now since the set B is inside set A, the subset concept comes with B being the subset of A, not the A subset of B, is how I understand through the diagrammatic form. In general, you can also understand the subset concept without the diagrammatic representation, because if all the elements of B get cancelled with A, then I can say that B is subset of A. Or if all the elements of A get cancelled with B, then I can say A is subset of B. Is the other way of understanding the concept through the shortcut means. So if all the elements of set B are getting cancelled with set A, yes, they are getting cancelled. Therefore, B is subset of A. Or going by the reverse process, if all the elements of A get cancelled with set B, then A is said to be subset of B. The rule is all the elements must get cancelled with the other set. If one element is left which doesn't get cancelled, then that one set will not be the subset of the other set, is how I understand the subset concept. So let's see an example problem of identifying the subset. Say for example, I have set A, or I take set P to be 1, 0, minus 3, minus 5, 9, and then the set Q minus 3, minus 5, 0, 1, 9, 10, 12. Then I want to identify the subset of one set with the other set. So immediately you can either use the Venn diagram, the diagrammatic representation, or done through the cancelling of each of the elements of the two different sets. So let me use the cancellation process where I cancel this with this, and the next this 0 with 0, minus 3 and minus 5. Now since all elements of P are cancelled with Q, this makes me understand that this is bigger than this set. Therefore, P is subset of Q. Therefore, I can immediately say that the set P is subset of set Q, or P is part of Q. Therefore, when I draw this with the Venn diagram, I get Q outside and then the set P inside Q. Is how I get the subset concept. Now, one thing we need to note here, the learning outcome I make out in the subset is that if A is subset of B, then A is the smaller set and B is the bigger set. So A subset B implies number of elements in A is less than number of elements in B, because this forms the bigger set and this forms the smaller set. The cardinal number of A is less than cardinal number of B. Secondly, I understand that if A is subset of B implies B is superset of A. Usually this is denoted with superset. So whenever A is subset of B, then I say that P is subset of Q, Q is superset of P. So in this case, I read this as B is superset of A. So if B is superset of A, then cardinal number of B will be greater than cardinal number of A, or the number of elements in B will be greater than number of elements in A. This is how I understand the subset and the superset concepts. Is how we understand. The third thing is all the sets of the given problem all the sets of the given problem are subsets of the universal set, because we already have taken the definition of the universal set to be the biggest set. Now, when universal set is the biggest set, all the different sets considered in that problem are subsets of or part of the given universal set. Therefore, all the sets of the given problem are subsets of mu, which we know that is the universal set. So these are the learning outcomes which we derive by understanding the concepts of subsets and supersets, is how I understand the subset and superset. Next, coming to this, the equal sets is usually derived from the subsets. Now that we have discussed about the subsets, let's see how the two sets are equal. Now, two sets are said to be equal and denoted with equality sign if A is subset of B is the first property and B is subset of A. The tendency of A subset of B and also equally at the same time B must be subset of A, then in that case the two sets are equal, is how we understand. Say for example, if I take the elements of A as 1, 3, 5, 7 and the elements of B as 7, 1, 5, 3. Now in this case, we first identify whether A is subset of B, then we cancel all the elements of A with B, and if nothing is left in A, then A is subset of B. So let's try with A with B. 1 and 1, 3 and 3, 5 and 5, 7 and 7. So none of the elements in A is left over and all are cancelled with B. Therefore, I can say that A is subset of B. And equally, when I go in the reverse process, I see that none of the elements of set B are left over when cancelled with set A. Also, equally makes me understand that when this is subset, B is also subset of A. Equally with 50-50 chances. A is subset of B and B is subset of A. Therefore, according to the definition of the equal sets, when A is subset of B and B is subset of A, that implies these two given sets, as out here in this example, are equal, is how I understand the equal sets. Now, what is the learning outcome we make in case of equal sets? As you see these two sets in the example problem, I see that both the sets have the same elements but taken in improper order. So when I take this, my first element is 1, but my second element is equally 1. My second element is 3, my fourth element is equally 3. The third element is 5, and the third element is equally 5, and the fourth element is 7, and my first element is 7. So it is nothing but the elements are equal in equal sets, but irrespective of the order. So I make the learning outcome here that A is equal to B implies all elements of A are same as all elements of set B in not in order. They may not be in order, but the elements when aligned in order definitely will be the same and the similar sets, and hence equal sets implies the elements of set A are same as elements of set B. We cannot have, and also the learning outcome, the most important learning outcome in equal sets is that when two sets are equal, then cardinal number of A is equal to cardinal number of B. That is, the number of elements in set A will always be equal to number of elements in set B if the two sets are equal, is how I understand the concept of equal sets as my learning outcome.